Today I will show you how to make the internet better for applications which cannot tolerate even short periods of unreachability, which is work that was done at UCL by me and my supervisors. So today users expect a constant end-to-end reachability when they use the network. For example, when I connect to a server, I expect my connection to behave as a physical direct line from me to the server. This is assured in two main ways today. We have reliable transport, which masks losses caused by congestion. And basically, when the topology changes, the routing system quickly adapts. Now, when any of those two things happen, there is a brief interruption to end-to-end reachability. Legacy applications have no problem with that. Things like file transfer or email can handle this gracefully. However, novel applications are less tolerant to those brief periods of interruption to reachability. Things like VoIP, things like interactive gaming or high-frequency trading. Now, traditionally, people have blamed congestion for causing packet drops and thus unreachability. While this is true, studies have shown that the routing protocols that the network is running or the routing system may also have a big impact and play a major role in causing packet loss. So how can we make the routing system better support interruption-intolerant applications? Well, to answer this, we must first take a look at the routing system. Let's look at the big picture. The internet is a collection of autonomous systems. They connect via iBGP sessions. iBGP is used to distribute external routes among autonomous systems, and iBGP stands for external BGP. Zooming in on a single autonomous system, there is internal connectivity within the autonomous system, which is maintained by an interior gateway protocol, or IGP, like OSPF or ISIS. There are border routers, which is where this autonomous system connects to the rest of the world. When an external route is received via eBGP at the border router, it may need to be distributed internally so that people within the autonomous system or other border routers know about it. This is the job of iBGP. Now, iBGP behaves exactly like eBGP. However, it runs within the autonomous system and distributes external routes internally. The intra-domain routing protocol, which is the big red IGP here, is only concerned when the topology changes. It is relatively stable. Link failures are not that common. And also, this is managed by a single entity, so management events can be scheduled accordingly. However, in any big autonomous system, there's a constant stream of external updates which need to be propagated using iBGP, which means that the iBGP is a lot less stable than the IGP. Okay, so we need to look at all three pieces of the routing system. There has been a lot of research on reliable and transient-free interior gateway protocols. There has also been previous research on improving eBGP, not only in terms of the usual suspects such as reliability, scalability, and configuration, but also improving eBGP in terms of reachability during convergence, looking at what happens while this external route is propagating. Now, work exists on the iBGP side, which relates to solving configuration problems and also avoiding things like path exploration. However, the fundamental behavior of intra-autonomous system route propagation is still unexamined. So what exactly happens during the propagation of the external route? This is what I will be talking about today. And let's look at iBGP. Well, in general, there are two main ways people use iBGP. The first one is called full mesh iBGP, and as the name suggests, there's a full mesh of sessions between everyone and everyone else. This scales badly, but is straightforward to configure. To fix the scalability problem in large deployments, people use route reflectors. Route reflectors add hierarchy. We will designate some of our routers to be reflectors. They will be fully meshed, and everyone else will be a client to one or more route reflectors. This reduces the number of sessions and makes it scale. However, the configuration becomes error-prone and is not even guaranteed to achieve the same solution as full mesh iBGP after converging. So where does exactly iBGP go wrong? Well, to see, let's take a look at this synthetic example. We only have 6 devices in the autonomous system. There's 2 border routers. And there is only one route for a single external prefix. During this talk, I will only be focusing on what happens with one prefix. This single route directs traffic for the prefix to use 5 currently to exit the autonomous system. In this case, there are iBGP sessions from the border routers to everyone else, and I'm only showing the sessions from 0. So let's look at what happens when 0 receives a better external route. Because the route is better than the current one, which is from 5, the new route will have to be distributed to everyone over the sessions shown. As the update propagates, loops may occur. In this case, 2 receives 0's update before 1, and because 1 still goes towards 5, and 2 now goes towards 0, traffic will transiently loop between 1 and 2. This is due to the lack of ordering between sessions. However, and also note that the IGP hasn't changed at all. There has been no topology change which triggered the loop. It was only caused by external events. So why should we care about those loops? Now, those are bound to be very transient because links are very fast and control traffic is usually prioritized. Turns out that this is not always the case. BGP processing happens in the control plane, which is a lot slower than the forwarding plane. Previous research has shown that processing delays of BGP updates can be in the hundreds of milliseconds, which is very significant, especially when talking about real-time traffic. There's one more thing. In addition, loops can also be very detrimental because when they happen, they can potentially affect other prefixes, not just the one the BGP update that caused the loop was for. To illustrate this, here we have 2 routers with 2 flows. Now, if a loop forms, the smaller flow will start growing, and it will eventually cause queues to overflow, which will hurt the other flow. Now, these side effects and the loops that I showed you are not just hypothetical. They have been previously observed in practice and indeed were found to have negative impact. So today I will present 2 protocols, SOUP, which stands for the Simple Ordered Update Protocol, which is a provably loop-free alternative to iBGP, which avoids the problem that I just showed. However, it can increase convergence times in some cases. And LOUP, the Link Ordered Update Protocol, which is an optimization of SOUP, which converges faster, but may very rarely loop. Now, let's start by fixing the little synthetic linear example that I showed you before. In general, we want to ensure some ordering constraint on the application of updates. We will do this in the simplest way possible. We'll have single hop sessions, and we will forward updates hop by hop. This gives us regions of contiguous updates, and as you can see, the updates propagate as sort of a wavefront. Now, this is what we call the Wavefront Property, and this is what SOUP uses to propagate information. And we use this to get basic ordering of updates. Now, this worked fine for the one-dimensional example, but what about more complex topologies? Well, here we have the same setup as before. However, we've added one more link, 1.3. This new link has a high metric and is not used when forwarding traffic. And you can see this from the forwarding paths. So in this case, we have a better update from 0. It will propagate to 1, and then it will get forwarded to both 2 and 3. And now we have a problem if this update gets to 3 before it gets to 2. We have a transient loop between 2 and 3. Now, 1.3 is not on the forwarding path. It should not have even been used to begin with to forward this update. So here's what the problem is in the general case. This is a diagram of a generic autonomous system with 2 border routers. Everyone is currently routing towards B. Here's the new update. It propagates as a wavefront. The little triangles show the direction of the propagation. And as it propagates, it causes routers to assume the new route. And now let's focus on 2 routers. Let's focus on X and Y. Y is on the forwarding path from X to A. However, X cannot really reach A in this example because Y still has not received the new route, and it will forward traffic towards B. Now, as a matter of fact, a loop may occur, which is what we previously observed, because X's traffic, which is now at Y, will try to get forwarded towards B by Y, and it may get passed back to X. Now, in general, what we need to do is we need to ensure that at any time along any forwarding path, there is only one switch of route. How can we enforce this? Well, simple. We'll propagate updates along the concatenation of the forwarding paths to the border router that originated the update. We call this the reverse forwarding tree, and this is the RFT routed at 0. This is what SOUP uses to send new and improving routes. This is nice because using the RFT now we can propagate improving information in a completely distributed loop-free manner, providing that the network topology is stable during propagation. So what about withdrawals? One can not only send updates, but can also send withdrawals or updates that make a route less preferred. How do we handle those? Well, here you can see a setup which is very common with peering. We have two equally preferred routes. They split the autonomous system in two pieces, and each router holds both routes. Again, we have two border routers. Now, let's look at what happens when 10 withdraws its route. We immediately have a problem. This is because 10 still keeps track of 0's route, and when it sees the external withdrawal, it will start directing traffic towards 0. However, 6, 7, 8, 9, and 11, they haven't heard the withdrawal yet. So they don't know that the route is no longer available and that they should go towards 0. Now, we have a transient loop which is guaranteed to happen, and it doesn't really go away until the withdrawal hits 5 or 6. Now, this is bad. We want to fix this. So in general, every time when there is more than one best route, BGP will split the autonomous system. In this case, there are two, and half of the autonomous system goes to A, the other half goes to B. Midline is the point where it costs in terms of internal metric as much to go to A as it costs to go to B. Now, here we can see the withdrawal coming from B, and here we can see this wave of transient loops that you previously saw. Now, how do we fix that? Well, the simplest and most obvious solution is to just not apply the withdrawal. Then we have no problem. It will simply propagate, and as it propagates, it doesn't change paths on intermediate routers. What we do is separate the reception of a routing update from its application to the forwarding table, which changes how packets are forwarded. We do not change how packets are forwarded. So we will let the withdrawal propagate, and then as soon as it hits the other end of the network, we want to start applying it. Now, the way we will apply it is we will apply it along the inverse of the propagation path from B. And you can see that as this happens, the network eventually converges. We call this reverse activation, and this is what SOUP uses when to activate worsening routes and withdrawals. Now let's see it in practice. This is the previous example. We have the withdrawal propagating. And here you can see that 9 and 11 can immediately apply it because they are the edges of the network. And they send activation to 8. However, 8 cannot change yet. It still is waiting on an activation from 7. Now, this activation from 7 will be received from 6, from 5, from 4, and so forth. Now, this is good because now, using this reverse activation, we have the ability to propagate worsening routes. However, is this all? Well, there is one more mechanism, and you can read about it in the paper. It allows for switching from reverse activation to regular activation, or propagation down the RFT. Now, what is important is that with this last mechanism, SOUP becomes provably loop-free at all instances if the underlying network topology is stable. There is proof in the paper, if you're interested. Now, there's a problem with SOUP. Well, going back to the reverse activation example, here we have the withdrawal propagating, and it doesn't change state. However, it should not really be the case that we need to propagate it towards the other end of the network. This is slow. We should be able to shortcut the activation from the midline. Now, how can we do this? Well, this is where LOUP comes in. LOUP is a superset of SOUP, It inherits all the mechanisms I've previously described, and it adds one more that we call tell me when messages. How do those work? Well, when a withdrawal propagates, we need a way to indicate when it has passed the midline, which is shown in red here. How can we do this? Well, simple. The property of the midline is that devices to one side of it go one way, and devices the other side of it go the other way. So we need to somehow trigger an explicit message that tells you when the router you're sending the withdrawal to is not using this route. Or in other words, we need to know when the withdrawal has crossed the line. We use what we call tell me when messages. In this case, 0 will send 1 to 3, 3 to 4, and so forth. The tell me when is piggybacked on the withdrawal, and it essentially says, tell me when you're not using the route that I'm using. So a router will reply when it's no longer using the route, or it wasn't using the route to begin with. And now the reply acts as activation. And this obviously results in faster convergence for the network. Now, to summarize, we have two protocols, SOUP, which is provably loop-free, but may delay convergence in the example shown, and LOUP, which fixes this, but in cases of unusually high churn may loop transiently. By churn, I mean very quick, less than 2 round-trip times in the network, succession of updates for the same prefix. Now, time for some evaluation. I will only show you graphs relating to loop freedom and delay. There is a lot more evaluation results in the paper. I decided to focus on loop freedom because this is what we promised at the beginning of the talk, and on delay because it illustrates the difference between SOUP and loop. There is another valid question, which is why do we need a new protocol to begin with? We already have a provably free IGP, which is called Duo, which is the basis of Cisco's EIGRP. Why not just use this and inject the external routes we have into this IGP? I will be presenting simulation results based on the topology of Hurricane Electric, which is a large international ISP. The loops that I will be telling you about are very dependent on variable delay. Now, in our experiments, we introduce no processing delay, and we model a propagation delay variation of maximum of 10 milliseconds. Therefore, we expect loops to last a lot longer in practice. Now, we also have real-world results in the paper from a prototype. Now, let's first look at iBGP with route reflectors. Initially, there is one route, and at 0.1 seconds, we introduce a better alternative. Now, on the y-axis here, you have the number of routers in a particular state. At any moment in time, a router can be in one of 4 states. It can be new exit, which means it's using the new route. It can be old exit, which means it's still using the old route. It can be marked as no route, which means that if it were to receive a packet in this instant in time, it would just drop it. And then it can be in the loop state, which means that the packet would loop. Now, what we do to generate those graphs is we take the topology, and we initially there is one route, and we inject a better one. Now, if we look at what happens at the end of the simulation, basically the network has converged and everyone has switched to using the new exit. However, iBGP with route reflectors in the meantime, it exhibits transients. It exhibits both black holes and loops. Now, loop, which is our protocol, it avoids both the loops and the black holes. To evaluate the delay incurred on withdrawal, we repeated the previous experiment. However, this time we initially have 2 routes breaking on IGP, and you can see the result of withdrawing one of them. This is a CDF of the median time it took for the network to converge over 100 runs. And you can clearly see the impact of the tell me when optimization here. And you can also see a curve for Duo, which is this loop-free protocol, IGP protocol I talked about. Now, in conclusion, iBGP's transient loops disrupt end-to-end reachability. We need careful ordering and application of routing changes in order to prevent loops. Now, I've presented a simple ordered update protocol, which is fully distributed and provably prevents all transient loops when the underlying topology is stable. It's also lightweight, and it's configuration-free. Now, I've also presented LOUP, which is an optimization of SOUP, which allows for faster convergence. Thank you.
Ethan Katz-Bassett, University of Southern California. So with the withdrawals, you're waiting to apply them essentially until you hear back that it's safe to apply them. Do you have any thoughts on what you should be doing with the packets that you're getting for the destination that's been withdrawn during that time?
That's a very good question. Well, there is this fundamental trade-off between whether you would loop or whether you would black hole. If you just don't do anything, what will happen is that the packets will just be dropped at the border router and it will black hole. However, you can be really smart about it, and if you already have a tunnel set up from this border router, because this border router really actually knows where the packet should be getting. If you have a tunnel already set up at this border router to the destination where the packets should be getting, you can just forward them using this tunnel, because you still have IGP connectivity.
Thanks.
Yep.
Hi, Mike Friedman, Princeton. I really like this work, and the animations were particularly nice.
Thank you.
I was actually wondering, it seems like LOUP, the problem was that you had two concurrent updates to the same prefix, and you also used this tell me, this shortcut. It wasn't totally obvious. I totally believe that there's a proof in the paper. It wasn't obvious why, if you did not use this tell me more shortcut, you might still not have strange issues in that the propagation for the reverse activation, if the announcements are coming from different parts of the network, the propagation for the reverse activation seemed like they could arrive in a different order.
Yep, definitely.
And that these things could be applied in different...
Yep, definitely. Now, in order to fix this, we have, as I showed, we have one more mechanism which we haven't discussed here.
Ah, that was the missing mechanism.
And this is, and it allows for switching from basically reverse activation to regular forward activation in the, in sort of in the middle of the network. And we do have a feasibility condition, which is much like Duo has one. And then you can read about it in the paper.
Okay, thank you.
Let's thank Nikola again.